we are going to need to calculate the derivatives of more complicated functions than simple powers of x. And we really don't want to rely on the definition of derivative and redo everything from scratch for every function we face. So we are going to develop some tools which provide shortcuts for dealing with combinations of functions. Given a function f of x, we can form new functions from it. For example, h of x equals k times f of x for any constant k. Or we can have two functions, f of x and g of x, and we can form new functions by taking sums, products, and ratios. S of x equals f of x plus g of x, p of x equals f of x times g of x, and r of x equals f of x over g of x. To make these ideas concrete, if f of x equals x to the 1/2 and g of x equals sine x, then we can multiply either of them by a constant, say k equals minus 3. Then we get new functions, h of x equals minus 3x to the 1/2, and j of x equals minus 3 sine x. We can also form sums, products, and ratios. S of x equals x to the 1/2 plus sine x. P of x equals x to the 1/2 times sine x, and r of x equals the ratio x to the 1/2 over sine x. This develops an entirely new group of functions, and if you doubt that these new functions are wildly different from the originals, I suggest you graph some of them. Now the fundamental question: if we know the derivatives of f and g, can we state the derivatives of these new functions? That's the question we're going to answer in this lecture. As an example, let's first find the derivative, f prime of x, of the function f of x equals square root x from the definition. We write the difference quotient for a point af of a on the graph of f. That's f of x minus f of a over x minus a, and is the slope of the chord or secant line between the nearby point xf of x and the given point af of a. We then calculate the limit of that difference quotient as x tends to a. The limit as x tends to a of the difference quotient is root x minus root a over x minus a. Using our reverse factorization tool, we multiply numerator and denominator by root x plus root a, which of course leaves the expression unchanged. When we carry out the calculation, we end up taking the limit as x tends to a of 1 over root x plus root a, and that turns out to be 1/2 a to the minus 1/2. So the derivative of f of x equal x to the 1/2 is f prime at x equals 1/2 x to the minus 1/2. Now suppose we want to calculate the derivative of h of x equals minus 3f of x. That's minus 3 square root x. We certainly don't want to go through the entire process again. If there is any justice in this world, it should be true that h prime of x is minus 3f prime of x. That is, it should be equal to minus 3/2 x to the minus 1/2. In plain English, constants should just factor out of a derivative, and in mathematical notation, it should be true that the derivative of kf of x is k times the derivative of f of x. Well, there is justice in this world. This statement is true. Here's the proof in 2 lines to settle the issue once and for all. We start by writing down the difference quotient for h of x at a point ah of a on its graph. H of x minus h of a divided by x minus a is just kf of x minus kf of a over x minus a, and the k factors right out of the difference quotient. Notice that we ended up with k times the difference quotient for f of x at the point af of a. Now to calculate the derivative of x at x equals a, we take the limit as x tends to a of the difference quotient. We can factor the k out of that limit by one of our list of limit theorems, the one that says that constants factor out of limits. But the remaining limit is exactly f prime at a, so we have proved that h prime at a is kf prime at a. If we look at the derivative of s of x equals f of x plus g of x, the principles involved are identical, and the result is that the derivative of f plus g is just f prime plus g prime. Let's go through the proof. We form the difference quotient for the function s of x equals f of x plus g of x, and we regroup the numerator so that we end up with, in the numerator, f of x minus f of a plus g of x minus g of a. In the denominator, we still have x minus a. Now we take the limit, and remember from our limit laws that the limit of a sum is the sum of the limits. So the derivative of this sum function, s prime at a, is the limit as x goes to a of f of x minus f of a over x minus a, plus the limit as x goes to a of exactly the difference quotient for g. In other words, we end up with f prime at a plus g prime at a. As an example, suppose for a moment that we have determined, as we certainly will very shortly, that the derivatives of p of x equals sine x and q of x equals x cubed are sine x prime is cos x, and the derivative of x cubed is 3x squared. In fact, let's just admit now that very shortly we shall prove the famous power law that the derivative of x to the alpha is alpha x to the power alpha minus 1. Or in words, bring down the power and take x to the next lower power. If you will accept these facts for now, then we can compute the following derivatives very easily. The sum minus 2x cubed plus 4 sine x has derivative minus 2 times 3x squared plus 4 times cos x. Notice that we had to use both of our new rules. First we separated the sum, and then we factored out the constants. Now if we accept the power law, we can find the derivative of any polynomial using these results. For example, the derivative of the polynomial 3x to the 10th minus 6x to the 5th plus 2x minus 11 is 3 times 10x to the 9th minus 6 times 5x to the 4th plus 2 times 1, which is the derivative of x, minus 0, which is the derivative of 11. In other words, it's 30x to the 9th minus 30x to the 4th plus 2. But in real-world applications, we need more. We need to find the derivative of a product of two functions and also the derivative of the ratio of two functions. In the cases of multiplication by a constant and addition of functions, the results were very intuitive, exactly what we expected. The product and quotient rules are definitely not intuitive. Here's the product rule. First, let's make the notation a bit more concise. Fg prime is f prime g plus fg prime. In other words, to differentiate a product, you have a sum, the derivative of f times g plus f times the derivative of g. Secondly, let's write this law in other notations for derivatives just to expose you to them. The d by dx notation looks like this, or more concisely, alternatively, it can be written in the capital D notation. And that notation sometimes uses capital D with a subscript x. In many courses, you are expected to be able to prove these rules, so we will look at the proof. But first, let's examine an example. The derivative of x squared sine x by the product rule is the derivative of x squared times sine x plus x squared times the derivative of sine x. And that means that the derivative of x squared sine x, the product, is 2x sine x plus x squared cos x. At this point, it's worth thinking about the power of abstract mathematics. You know the value of the slope of the tangent line to the graph of the function h of x equals x squared sine x at any point on its graph. It's exactly 2a sine a plus a squared cos a. For example, at the point pi 0, which certainly lies on the graph since the sine of pi is 0, the slope of the tangent line is minus pi squared. Since minus pi squared is around minus 9.87, we see that the slope of the tangent line is very steep and negative. So we know, without doing any graphing, that the function is rather rapidly decreasing at this point without drawing a single picture. The product rule also allows us to differentiate powers of functions. For example, by realizing that f of x squared is just f of x times f of x, you can write the derivative of f of x squared as the product, f times f differentiated, and that's f prime times f plus f times f prime. In other words, just twice f of x, f prime of x. But you can continue. You can interpret f of x cubed as the product of f of x and the square of f of x, and compute the derivative of f of x cubed is the derivative of the product of f of x with f of x squared. And using the product rule, that is f prime times f squared plus f times the derivative of f squared. And we write that out using what we just derived earlier, and we get f prime times f squared plus f of x times the derivative of f squared, which is 2f f prime. And when we clean it all up and collect terms, we find the derivative of f of x cubed is 3f squared f prime. We know that x squared prime is twice x. And now we know that f squared prime is twice f prime. Is there a connection? Yes. In fact, the power law for functions states that the derivative of f to the nth power is n, f to the n minus first power, times f prime. We could prove this now by induction, but we will delay the proof until later when we'll use a different method. Now for a proof of the product rule. Start with the difference quotient for the product function h of x equals f of x g of x. So you write down h of x minus h of a divided by x minus a. And that's just the product, f of x g of x, minus the product f of a g of a, all divided by x minus a. Now we have to try to evaluate the limit as x goes to a of the f of x g of x minus f of a g of a over x minus a. We are given that f and g are differentiable, so the limits of their difference quotients both exist. That is, f prime at a is the limit as x tends to a of the ratio f of x minus f of a over x minus a, and g prime of x is the limit again of a similar ratio in g. We can relate this information to the limit which gives fg prime by a clever device of adding and subtracting the same term from the numerator. We write down fg, the derivative, at a, is the limit as x tends to a of fg at x minus fg at a, and then we add and subtract f at a g of x minus f at a g of x, which is just 0, so we haven't changed anything. Now we can collect terms, do some factoring in the numerator, and use the fact that the limit of a sum is the sum of the limits. And what you end up with is that fg prime at a is the sum of two limits. The first limit is the limit as x tends to a of the difference quotient for f times g of x. And the second limit is the difference quotient for g times f at a. Now you can use the fact that the limit of a product is the product of the limits, so that fg prime at a is the limit as x tends to a of g of x times the limit of the difference quotient for f plus f at a times the limit of the difference quotient for g. And that should be g of a f prime at a plus f at a g prime at a. So our proof of the product rule is complete. Or is it? Can you spot the place where I made an unproved assumption? It's in the last step, where I replaced the limit as x tends to a of g of x by g at a. In other words, I assumed that since g is differentiable at x equal a, it must be continuous at x equal a. So we need to prove a small theorem. In fact, it's so small we call it a lemma. And it says if g is differentiable at x equal a, then g is continuous at x equal a. The proof goes like this. We are given that the limit of the difference quotient exists. So the limit as x goes to a of g of x minus g of a over x minus a is the number g prime at a. This means that that difference quotient gets closer and closer to the value of the derivative at a as x approaches a. We can write this as follows. The ratio g of x minus g of a to x minus a is equal to g prime at a plus something which gets smaller and smaller and goes to 0 as x goes to a. We do have a shorthand notation for this ridiculously long statement, and we may as well introduce it now to avoid having to write it again. If an expression e of x goes to 0 as x goes to a, we write this as e of x equals little o of 1 as x goes to a. This notation was introduced by the English mathematician J.E. Littlewood of Cambridge University, who just got tired of writing out phrases like the above. So now we can write g of x minus g of a divided by x minus a is g prime at a plus little o of 1. And if we multiply both sides by x minus a, we have g of x minus g of a is g prime of a times x minus a plus little o of 1 times x minus a. Now you can take limits and use the limit laws. The limit as x goes to a of g of x minus g of a is the limit as x goes to a of x minus a times g prime of a, factoring out the g prime of a, plus the limit as x goes to a of little o of 1 times the limit as x goes to a of x minus a. And everything in that sum goes to 0. So indeed, g is continuous at x equal a, and by proving this lemma, we have finally nailed down the proof of the product rule. Now we need to look at the derivative of the ratio of two functions. If we can differentiate two functions, f and g, then we need a theorem which tells us how to compute the derivative of the ratio r of x equal f over g. Here it is, and it's called the quotient rule. R prime of x, that is f over g prime, is f prime g minus f g prime over g squared. Very unintuitive. As an example, the derivative of x squared divided by sine x is the ratio of 2x sine x minus x squared cos x to sine squared x. Here is a statement of the quotient rule and other notations. d by dx of f over g is df dx times g minus dg dx times f over g squared. In capital D notation, it's even simpler. Capital D of f over g is d of f times g minus f times d of g divided by g squared. For the proof of this rule, we are going to introduce a slightly different notation for the difference quotient. Instead of computing the derivative at x equal a by using the slope of the chord line through a r of a and the nearby point x r of x, we are going to compute the slope of the chord line through the point x r of x and a nearby point x plus h, r at x plus h, and then let h go to 0. This more sophisticated notation just corresponds to renaming the 2 points that we use for the slope calculation. Here is a picture. So the slope of the chord line is r at x plus h minus r at x over x plus h minus x. And that's just r at x plus h minus r at x over h. And the limit which gives the derivative can now be written r prime at x equals the limit as h goes to 0 of r of x plus h minus r of x divided by h. An important point. The nearby point has coordinates x plus h, r at x plus h, not x plus h, r of x with h added to it. As an example, let's calculate the derivative of p of x equals x cubed using this new notation. P prime of x is the limit as h goes to 0 of p at x plus h minus p at x over h. And that's the limit of x plus h quantity cubed minus x cubed over h. Now you carry out the cube, and you get x cubed plus 3x squared h plus 3xh squared plus h cubed minus x cubed. And you're dividing by h. The x cubes cancel. You divide through by the h, and you get the limit as h goes to 0 of 3x squared plus 3xh plus h squared. And the limit is clearly 3x squared. The more sophisticated notation bypasses the use of the symbol a and gives us the derivative directly as a function of x. So now to compute the derivative of r of x equal f of x over g of x, we form that difference quotient, r of x plus h minus r of x over h. And that's the ratio f of x plus h divided by g of x plus h, minus that same ratio evaluated at x, all divided by h. We put it over a common denominator, and it doesn't look very useful. The numerator is f of x plus h g of x minus f of x g of x plus h, and the denominator sort of looks like h times g squared, except it's really g of x times g of x plus h. Now we do the old add and subtract trick to get ratios that look like difference quotients for the functions f and g. The term we add and subtract in the numerator is f of x g of x. And when we do that, adding and subtracting that product, and do a little factoring and cleaning up, we get exactly 1 over g of x times the limit as h goes to 0 of f of x plus h minus f of x divided by h, times the number g of x, times the limit as h goes to 0 of 1 over g of x plus h. And then we have added to that the term f of x times the limit g of x minus g of x plus h divided by h times the number 1 over g of x times the limit as h goes to 0 of 1 over g of x plus h. So it's a real handful of terms, but they're very easily evaluated. And when you clean it up, you get f prime g of x minus f of x g prime of x, all divided by g squared, exactly as we wanted. Now you might ask, where did the minus sign come from in the f of x g prime at x? Well, go back and look at the difference quotient that gave you g prime, and it's written backwards as g of x minus g of x plus h. That's the way the algebra worked out. And so to turn it around, you have to multiply it by minus 1, and then in order not to change things, you have to put a minus 1 out front. Notice again, we needed the fact that f and g are continuous because they are assumed differentiable. One can use the quotient rule to differentiate the reciprocal of a function. Since the reciprocal, q of x equal 1 over f of x, is just the ratio of the constant function 1 and the function f of x. By the quotient rule, q prime is the derivative of the ratio 1 over f of x. And that's the derivative of 1 times f of x minus 1 times f prime at x, all divided by f squared. Of course, the derivative of 1 is 0, and so you end up with minus f prime over f squared. As an example, the derivative of the cosecant function, that's the derivative of 1 over sine x. And so that's equal to minus 1 over sine squared times cos x, which is the same as minus cosecant cotangent. To conclude, let us summarize our work in this lecture. We have developed the following computational rules for derivatives. The product rule, fg prime is f prime g plus fg prime. The quotient rule, the derivative of f over g is the ratio f prime g minus fg prime divided by g squared. And we've developed some consequences of these rules, namely the power rule for functions, that the derivative of f to the nth power is n f to the n minus 1 power times f prime, and the rule for reciprocals of functions, the derivative of 1 over f is minus f prime over f squared. We also established the important fact that if a function is differentiable at a point, then it is continuous at that point. We're going to develop two of the most powerful tools available for computing derivatives, the chain rule and the rule for differentiating the inverse of a function. First, the chain rule. This is a tool for differentiating a composite function. To get started, we want to review this sophisticated and powerful concept. Let's begin with an example from pure mathematics. Consider the function c of x equals the square root of sine x, and restrict x to the interval 0 pi so that the function sine x is non-negative. To calculate this function, you first compute y equals sine x. And since y will be non-negative for x in the given domain, you can then calculate c of x equals square root of y. In other words, the calculation of values for c of x is a composition of two functions, namely the function f of y equals square root y, and g of x equals sine x. And you can write c of x equals f small circle g of x, or you can write c of x equals f parenthesis g of x. You can also sketch the process of computing c of x as a sequence of mappings. Composite functions are very common in the real world. Here's a very simple example. A person applying for social assistance must first declare their income. So the social worker first computes I of P, the monthly income, for a given person P. On the basis of the value of I of P, the social worker then computes the amount of assistance available. In other words, the assistance function is A of I of P. The chain rule is the rule for differentiating a composite function. If you know f prime and g prime, can you calculate the derivative of f composition g? The answer is that the derivative of f of g of x at a is f prime at the point g of a times g prime at a. Be sure to be able to state this in words, because mistakes are easy to make if you don't have a clear idea of what it is saying. In plain English, it says, to compute the derivative of f composition g at a point x equal a, first compute the derivative of the function f at the point g of a, and form the product of this derivative with the derivative of g at the other point a. In other notations, the derivative with respect to x, capital D subscript x, of f composition g, evaluated at a, is df at g at a times dg at a. Or d by dx of f of g of x is df dy at y equal g of a times dg dx at x equal a. As an example, consider the function square root x squared plus 2x plus 3, which is f composition g with f of y equal the square root of y, and g of x equals x squared plus 2x plus 3. Then, f prime of y is 1/2 y to the minus 1/2, and g prime at x is 2x plus 2. And the chain rule says that the derivative of the square root of x squared plus 2x plus 3 at x equal a is 1/2 y to the minus 1/2 times the derivative of g, which is 2a plus 2. But you have to replace y by g at a, which is a squared plus 2a plus 3. So replacing a by x now, the derivative of x squared plus 2x plus 3 square root is 1/2 x squared plus 2x plus 3 to the minus 1/2 times 2x plus 2. Another example. Let's look at h at x equals the sine of 3x plus 1. That's f composition g of x with f of y equals sine y, and g of x equal 3x plus 1. F prime of y, then, is cos y, and g prime at x is 3. Then h prime at x, the derivative of the composite function, is cosine 3x plus 1 times 3. One way to avoid errors is to think of peeling off and differentiating the functions one layer at a time, starting at the outside and leaving anything inside each layer unchanged. In the last example, we had h of x equals sine 3x plus 1. So we differentiate the sine function, but leave the expression inside unchanged. Then multiply this result by the derivative of what is inside. The derivative of the sine of 3x plus 1 is the cosine of 3x plus 1 times 3. If you have 3 layers, the idea is the same. Peel off one layer at a time and don't change what is inside the layer. For example, the derivative of sine of square root of 3x plus 1 is, differentiate the sine to get cosine of square root 3x plus 1, then multiply that by the derivative of square root 3x plus 1. And then we continue. We have the cosine square root 3x plus 1 times 1/2 3x plus 1 to the minus a half. That's the derivative of the square root function with the stuff inside unchanged. And then we multiply that by the derivative of what is inside the square root function, 3x plus 1, which is 3. We are going to give a mildly incorrect proof of the chain rule because this incorrect proof is far more instructive than the careful proof. We will confess and point out the error after we have gone through it and outline how to correct it. To begin, we as usual write down the difference quotient for f composition g. That's f of g of x minus f of g of a over x minus a. Now we have to take the limit as x goes to 0, but we need to get the derivative of f involved here somehow. So we multiply the numerator and denominator by g of x minus g of a and group the single fraction into 2 separate fractions. So we get f at g at x minus f at g at a divided by g at x minus g at a times g at x minus g at a over x minus a. Now we take the limit of our difference quotient and use the product rule for limits. The limit as x goes to a of that product is the product of the 2 limits, and the first limit is f of g of x minus f at g at a over g at x minus g at a, and the other limit is g at x minus g at a over x minus a. Now the last limit in this product is just g prime at a, exactly what we wanted. We need to show that the first limit in this product is exactly f prime of y at the point g at a. Since g is assumed differentiable, it follows that g is continuous. This means that if you set y equal to g of x, then the limit as x goes to a of y is g of a. So you can write this limit as the limit as y goes to g of a of f of y minus f at g of a over y minus g of a. And that's exactly the derivative f prime at the point g of a. So this seems to complete the proof of the chain rule, but there is an error. The problem is at the beginning of the proof, when I multiplied the numerator and denominator by g of x minus g of a. This could very well be 0, making my calculation meaningless since 0 over 0 is undefined. There are several ways to fix the proof, all of them quite tedious and not very enlightening at this stage in your career. If you want to skip the next argument, that is perfectly okay. Perhaps the least painful approach is the use of the little o1 notation for an expression which goes to 0 as x goes to a. We can write the relationship between the difference quotient and the derivative as the difference quotient, g of x minus g of a over x minus a, is g prime at a plus little o of 1, where little o of 1 just stands for something that goes to 0 as x goes to a. Similarly, for f of y, you can write that the difference quotient, f of y minus f at g of a over y minus g at a, is f prime at g at a plus little o of 1, meaning some different function, of course, that goes to 0 as x goes to a. All we care about is that these expressions go to 0. We don't care what they are. Now the trick is to multiply each of these equalities, respectively, by x minus a and g of x minus g of a, clearing those denominators. This gives you g of x minus g of a is g prime at a x minus a plus little o of 1 times x minus a. And the second equation gives you f of y minus f at g at a is f prime at g at a times y minus g at a plus little o of 1 times y minus g at a. And these two new expressions are even valid when y minus g of a, that is g of x minus g at a, is 0. Then we go back to the limit which defines the derivative of the composite function and plug in these expressions for respectively g of x minus g of a and the composite function f composition g at x minus f composition g at a. The result is a horrendously long expression. And if you clean that up and take the limit as s goes to a, it very clearly gives you f composition g prime at a is f prime at g at a, g prime at a. Now we can return to more practical things. The next and final tool to be discussed in this lecture is the rule for differentiating an inverse function. If we can compute f prime at a, can we determine the derivative of the inverse function at the point f at a? The picture shows what we have in mind. We are not going to prove that the inverse function is automatically differentiable at the point b equals f of a when f is differentiable at a, since this would be a major digression. We will just accept this result for now. The rule for computing the derivative of the inverse function is, if f of x is differentiable at x equal a, then the inverse function, f inverse of y, is differentiable at the point b equal f of a, and has the value f inverse prime at b is 1 over f prime at a, the reciprocal. In plain English, the derivative of the inverse function, f inverse, at a point b equal f at a is the reciprocal of the derivative of f at the preimage a. If we are given a table of values for f of x and its derivatives at certain points, then we automatically know the values of the derivative of the inverse function at the image points. For example, given the table of values as indicated, then we know the values of the inverse function at the points y equals 0, 3, 6, the image points of the points x equal 1, 2, and 3 under the mapping f. Specifically, f inverse of 0 is 3, f inverse of 3 is 2, f inverse of 6 is 1. The rule for the derivative of the inverse function enables us to calculate the value of the derivative of the inverse function at these points. For example, the derivative of f inverse at the point 0 is 1 over the derivative of f at the preimage point 3. Now that derivative was 10, so the derivative of f inverse at 0 is 1 over 10. Similarly, the derivative of f inverse at 3 is 1 over the derivative of f at the preimage point 2, and that turns out to be 1/3. And the derivative of f inverse at 6 is 1 over the derivative of f at the preimage point of 6, 1, and that turns out to be -1/2. We can use the original table to construct a table for the inverse function and its derivative. When dealing with functions defined by formulas, the situation is more subtle. Consider the function f of x equal x to the 1/3. Then it is easy enough to compute the inverse directly. F inverse of y is y cubed, and the derivative of f inverse of y is 3y squared. On the other hand, the inverse function rule states that the derivative of f inverse at a point y is the reciprocal of the derivative of f at the preimage point x. And we know the derivative of f at any point is 1/3 x to the minus 2/3. That's in the denominator, so it comes up into the numerator, and we conclude that the derivative of f inverse at y is 3x to the 2/3, which looks a little confusing. But y equals x to the 1/3, so 3y squared is 3x to the 2/3. The two formulas are equivalent. The proof of the inverse function rule is embarrassingly easy, making use of the powerful chain rule. We just recall that the composition of a function and its inverse gets you back where you started. That is, f of f inverse of y gives you y. F inverse applied to f of x gives you x. So we take the second of these formulas and we differentiate both sides with respect to x. And we get the derivative of f inverse composition f is equal to the derivative of x, which is 1. Now use the chain rule on the left. The derivative of f inverse at the point f of x times the derivative of f at x is 1. And that's equivalent to saying the derivative of f inverse at the point f of x is 1 over the derivative of f at the point x.